Have you ever stood outside on a clear night, looked up at the stars, and felt a sense of awe mixed with something else, something like curiosity, or maybe even suspicion? That quiet, persistent feeling that there's more going on up there than we've been told. You're not alone. For centuries, humanity has gazed into the cosmos with a mix of wonder and questions that grow deeper and more intriguing the more we learn. Because what if I told you that much of what we think we know about space, the vast, silent expanse above us, might not be the full story? What if the universe is keeping secrets, and some of the most profound clues have been hiding in plain sight all along? From the unexplainable silence that greets our attempts to contact other civilizations, to the strange, almost intelligent signals that arrive from the void without warning, there are hints, subtle, compelling, and often unsettling, that suggest our understanding of reality might be built on incomplete or even intentionally limited foundations. We've been taught that space is empty, that it follows predictable rules, and that with enough science and technology, we can unravel all its mysteries. But what if the rules themselves are part of the mystery? What if the silence isn't just emptiness but a message? What if the anomalies astronomers keep brushing aside are actually clues, pointing toward truths so profound they could redefine not just science, but our very place in the cosmos? In this video, we're going to explore 21 unwritten clues that space might not be what we think. We'll journey through cosmic paradoxes, dive into unexplained phenomena, and examine theories that venture to the edge of known science and beyond. This isn't about wild speculation. It's about looking closely at the evidence that doesn't fit, the data that challenges convention, and the possibilities that invite us to think bigger. By the end, you may not have all the answers, but you'll see the night sky differently. You'll understand why so many are beginning to question the narrative, and you might just find yourself wondering what else is out there, waiting to be discovered. So settle in, open your mind, and get ready to see the universe in a whole new light. But let's begin with perhaps the most profound and deeply unsettling mystery of all, a puzzle so vast it encompasses the entire cosmos, the Fermi Paradox. Named after the physicist Enrico Fermi, who during a casual conversation in the 1950s famously asked, "But where is everybody?" This paradox highlights the stark contradiction between the high probability of extraterrestrial life and the complete, deafening silence we receive in return. Consider the numbers for a moment. Our galaxy, the Milky Way, is home to an estimated 100 billion stars. Many of these stars are now known to host planets, with current estimates suggesting there are more planets in our galaxy than there are stars. And when we look beyond to the observable universe, the number of galaxies themselves is also in the hundreds of billions. The sheer statistical probability seems overwhelming. With so many worlds, so many potential incubators for life, it feels almost mathematically inevitable that we are not alone. The universe should be teeming with life, buzzing with the radio chatter and technological signatures of countless civilizations. Yet, when we point our most powerful radio telescopes to the heavens, what we hear is nothing but a cosmic hiss, the natural background radiation of the universe. It is an eerie, profound quiet. This silence isn't just an absence of sound, it's an absence of evidence where we most expect to find it. For over 60 years, projects like SETI, the search for extraterrestrial intelligence, have been meticulously scanning the skies, listening for any pattern, any signal that stands out from the natural background. And while there have been a few tantalizing blips, like the famous "wow" signal we'll discuss later, nothing has ever been confirmed or repeated. It's as if we're shouting into a canyon expecting an echo and hearing only the wind in return. This great silence forces us to confront some truly staggering possibilities. Perhaps advanced civilizations are incredibly rare, and the hurdles for life to not only begin but to evolve and survive for millions of years are so immense that most are filtered out by what scientists call the great filters. These could be existential catastrophes. Maybe every advanced culture eventually creates the technology that leads to its own destruction, whether through war, environmental collapse, or a mishap with artificial intelligence. In this grim scenario, the silence is a cemetery. We're not hearing from anyone because no one else made it. Other theories are even more mind-bending. What if they are out there, but they are so advanced that we simply cannot perceive them? Their technology and methods of communication could be as far beyond our understanding as a smartphone is to an ant. They might be using neutrino communication or manipulating space-time itself in ways we can't yet detect. Or perhaps they have chosen to remain silent, a concept known as the zoo hypothesis. This idea suggests that Earth is being intentionally isolated, placed under a kind of cosmic quarantine or preservation order by a galactic community, waiting for us to reach a certain level of maturity or peace before making contact. The silence, then, is a test. There's another, more unsettling thought. What if the universe is fundamentally dangerous for intelligent life? Maybe there is something out there, a predatory civilization, a berserker probe, or a natural cosmic phenomenon that makes broadcasting your location to the galaxy an exceptionally bad idea. In this scenario, every wise civilization goes dark, listening carefully but never transmitting, hiding in the stillness for its own survival. The silence isn't empty, it's hiding. It's a warning we haven't yet learned to decipher. This first clue, the Fermi Paradox, doesn't just ask about aliens. It holds up a mirror to humanity itself, forcing us to question our future, our technology, and our place in a cosmos that seems to be listening as intently as we are. And then, decades into that profound and puzzling silence, we heard something. It wasn't a drawn-out conversation, but a shout, a single, powerful burst of sound that came and went in little more than a minute, leaving behind one of the most enduring and tantalizing mysteries in the search for cosmic company. This is the story of the wow signal, an event so striking it was named for the exclamation a stunned astronomer scrawled in the margin of a date to print out. On August 15, 1977, the Big Ear radio telescope at Ohio State University was performing its routine scan of the heavens, part of the ongoing SETI search. It was listening to a specific frequency, 1420 MHz, which is in a protected band. This frequency is special because it's naturally quiet. It's the emission frequency of hydrogen, the most common element in the universe, and scientists have long reasoned that an intelligent civilization might use it as a natural, universal beacon to signal its presence. It's like choosing the clearest channel on a cosmic radio dial. For 72 seconds, the telescope's receiver locked onto a signal so powerful, so perfectly aligned with this ideal frequency, that it defied all conventional explanation. The signal didn't drift as a signal from a passing satellite or aircraft would. It didn't splatter across multiple frequencies, which is the telltale signature of earthly interference. It was a pure, narrowband tone, rising and then falling in intensity exactly as you would expect from a distant, fixed source passing through the telescope's stationary field of view. In every technical sense, it matched the precise profile of an artificial transmission originating from deep space. The astronomer on duty, Jerry Amon, circled the alphanumeric code representing the signal's incredible strength, 6EQUJ5, and beside it, he simply wrote, "Wow." That single word of astonished annotation gave the event its immortal name. The immediate and obvious question was, and still is, what was it? The signal appeared to originate from the direction of the constellation Sagittarius, near the star group Chi Sagittarii, in a region seemingly devoid of any known planetary systems or obvious cosmic radio sources at that time. The hunt for a repeat began almost immediately. If it was a genuine signal from an intelligence out there, you would expect to hear it again. Perhaps it was a beacon sweeping through the galaxy, and we had simply caught a fleeting glimpse as it passed by our celestial neighborhood. Astronomers pointed every available instrument toward that patch of sky, listening intently for decades. They scanned that same frequency over and over again with ever more sensitive equipment. But the silence returned. The wow signal never repeated, not once. This singular nature is what fuels both the mystery and the speculation. If it wasn't them, then what was it? The list of natural explanations is surprisingly short and unsatisfying. Some proposed it was a comet, but the known comets in that area weren't discovered until years later, and their hydrogen clouds are broad and diffuse, not sharp and focused. Others suggested it was a random burst of static from a passing human satellite, but a detailed analysis of satellite orbits from that era has failed to turn up a convincing culprit. The signal was simply too clean, too perfect. A simple glitch in the telescope's own electronics also seems unlikely, as the Big Ear had two separate receivers, and the signal was detected by only one of them as it traveled across the sky, which is exactly how a genuine external signal would behave. So we are left with a handful of profound possibilities, each more staggering than the last. Perhaps it was a one-time event, a natural astrophysical phenomenon we have yet to discover or understand, a cosmic burp of sorts, something that emits a brief, impossibly perfect radio scream and then vanishes forever. Or maybe it was indeed artificial. It could have been a powerful, targeted beacon from a distant civilization, a message meant for someone else that we just happened to intercept for a fleeting moment as we drifted through its path. Think of it like hearing a single, clear shout from a ship far out in a foggy ocean. You heard it, you know it was real, but you have no idea what it meant or where it came from, and it never calls out again. Another, more haunting idea is that it was a message meant specifically for us, a deliberate ping to see if we were listening, and when we failed to reply or even recognize it for what it was in time, they simply moved on. The wow signal stands as a ghost in the machine, a brief crack in the cosmic silence that proves we might indeed have neighbors, but that communication could be infinitely more complex and transient than we ever imagined. Just when we think we're starting to map out the strange sounds of the cosmos, the universe throws an even more baffling phenomenon at us, one that makes a single shout seem almost simple. Imagine, if you will, the most powerful energy release you can conceive, something that in a single millisecond, a mere thousandth of a second, can outshine 500 million suns. Now imagine that this titanic flash of energy, this cosmic lightning strike, is a radio wave, and it's traveling across millions, even billions, of light years of space to be captured by our dishes here on Earth. This isn't science fiction. This is the reality of fast radio bursts, or FRB, and they are one of the most active and perplexing frontiers in modern astronomy. The story of their discovery is a classic tale of finding something extraordinary while looking for something else entirely. The first known FRB was detected in 2007, not by a human astronomer in real time, but buried in the archival data from the Parkes Radio Telescope in Australia. It was a blast of radio waves so intense and so brief that for years, many in the scientific community dismissed it as a one-off glitch, perhaps a malfunction in the telescope's microwave oven. But then more were found. To date, hundreds of these events have been catalogued, and each one presents a monumental puzzle. They arrive without warning from random points across the sky, and their incredible brevity, lasting just a few milliseconds, makes them incredibly difficult to catch and almost impossible to pinpoint in the moment. What makes FRBs so deeply mysterious isn't just their power or their distance, it's their behavior. We've learned that they come in two distinct flavors. There are the one-off FRBs, which appear to be singular, catastrophic events. A colossal explosion of some kind that tears through the fabric of space, sends out this unimaginable pulse of energy, and then is gone forever, leaving no trace behind. Then there are the repeaters. These are sources that, from the same patch of sky, fire off multiple bursts. They can be sporadic, going silent for years before suddenly activating again, or they can be periodically active, like a cosmic geyser erupting on a semi-regular schedule. This dichotomy alone is a massive clue that whatever is causing these phenomena, there might be multiple, completely different engines at work. The hunt for a natural explanation has led astrophysicists to some of the most extreme objects in the universe. The prime suspects are magnetars, which are a type of neutron star with a magnetic field SO Chinese letter. It's almost beyond comprehension. Trillions of times more powerful than Earth's magnetic field, the stresses on the crust of a magnetar can cause starquakes, catastrophic ruptures that could, in theory, release those colossal bursts of energy we see as FRBs. Another compelling idea involves the collision of incredibly dense objects, like two neutron stars merging in a spectacular kilonova explosion. The physics of such an event could certainly generate a powerful, one-time radio blast. But the natural explanations, as compelling as they are, start to strain under the weight of some of the data. For instance, one particular repeating FRB, known as FRB 121102, has been localized to a small, dwarf galaxy over 3 billion light-years away. It's not just that it repeats, it's that it has been doing so for years, which rules out a one-time cataclysm like a collision. The energy required for such a sustained output is staggering. Furthermore, some bursts show an effect called Faraday rotation, meaning they've twisted through an immensely powerful magnetic field on their way to us, which fits perfectly with the environment around a magnetar. This seems like a solid case until you consider another repeater, FRB 20,200,120e, which was found not in a distant dwarf galaxy, but lurking right here in our cosmic backyard, inside the globular cluster of our neighboring galaxy, Messier 81. This environment is ancient and should be devoid of the young, violent stars like magnetars that are thought to create them. So why is it there? The very presence of an FRB in such an unexpected place forces us to question if we truly understand the mechanics at all. This gap in our understanding is where the most speculative and, frankly, the most thrilling possibilities emerge. Could some FRBs, particularly the precise, repeating ones, be something other than natural? The idea that they could be evidence of advanced technology is not one scientists take lightly, but it is one they are increasingly willing to discuss as a remote possibility. The sheer energy output is on a scale that could be imagined for a truly astronomical engineering project. Perhaps they are power beams for interstellar light sails, propelling gigantic spacecraft across the gulfs between stars. A single millisecond burst could push a sail to incredible speeds, or maybe they are some form of cosmic communication, a beacon system so advanced that its basic hello appears to us as a shattering blast of raw power. The fact that they are in the radio spectrum, the very band we use for communication, is at least a curious coincidence. They could even be the signatures of propulsion systems or energy generators from a Type 2 or Type 3 civilization on the Kardashev scale, operating on a level so far beyond our own that their everyday technology appears to us as brief, universe-spanning fireworks. While the natural explanations are always the most probable, the persistent mystery of fast radio bursts ensures that we must keep our minds open to all possibilities, reminding us that the universe is capable of generating wonders that continually challenge the limits of our imagination. And while bursts of energy from the depths of space present one kind of mystery, a far more subtle and insidious puzzle was quietly unfolding much closer to home, not with a bang, but with a barely perceptible whisper of a slowdown. This clue didn't arrive as a flashy signal. It was discovered in the painstakingly precise tracking of two human-made pioneers venturing into the unknown. The Pioneer 10 and 11 spacecraft, launched in the early 1970s, were triumphs of engineering, the first human objects to travel through the asteroid belt, the first to make close-up observations of Jupiter and Saturn, and the first set on a trajectory that would eventually take them out of our solar system entirely. They were marvels of navigation, their paths calculated with exquisite care using the well-tested laws of gravity and motion laid down by Newton and refined by Einstein. For years, everything went exactly as planned, but as these twin explorers journeyed beyond the orbit of Pluto, drifting into the cold, dark frontier of interstellar space, a tiny, persistent anomaly began to appear in the data. The engineers and scientists at NASA, a Jet Propulsion Laboratory, who were monitoring the spacecraft's telemetry with extreme precision, noticed something was off. By carefully tracking the Doppler shift in the radio signals bouncing back from the distant probes, the same principle that makes a siren change pitch as it passes you, they could measure the probe's velocity down to an astonishing accuracy. And what they found was baffling. Both Pioneer 10 and Pioneer 11 were experiencing a very slight but very real, unexplained deceleration. It was as if an invisible hand was reaching out and ever so gently applying the brakes. This wasn't a sudden jolt, it was a continuous, tiny sunward tug, a force equivalent to about 10 billion times weaker than the gravity we feel on Earth. To put it in perspective, it was like the gravitational pull you'd feel from a single sheet of paper resting in the palm of your hand. Minuscule, yes, but for the precise equations of orbital mechanics, it was a glaring error. The probes were falling behind their predicted trajectories by thousands of miles each year. This was the Pioneer anomaly, and for over 2 decades it stubbornly refused to go away. The immediate and most thrilling possibility was that this was a sign of new physics. Perhaps our understanding of gravity itself was incomplete on the largest scales. Maybe the inverse square law, which states that gravity weakens with the square of the distance, needed a slight modification for the vast, empty reaches of the outer solar system. Some theorists proposed that this could be evidence for exotic ideas like the existence of unseen dark matter halo surrounding our solar system, exerting a subtle gravitational drag. Others wondered if it was a hint of something even more profound, like the influence of higher dimensions as predicted by string theory, where gravity could leak into other dimensions, making it appear slightly weaker over immense distances. For a time, the Pioneer anomaly became a beacon for those who believed that a revolution in physics was waiting for us in the deep, quiet dark between the planets. The solution, when it finally came, was not from the realm of exotic physics, but from the world of meticulous engineering and humble self-reflection. A dedicated team of researchers spent years recovering old telemetry data, original design documents, and even consulting with the retired engineers who built the probes. They built an incredibly detailed computer model of the Pioneer spacecraft, accounting for every known force acting upon it, no matter how small. The key, it turned out, was heat. The pioneers were powered by radioactive thermoelectric generators, which produced electricity from the heat of decaying plutonium. This heat had to be dissipated, and it was radiated away from the spacecraft's surface. The team realized that this radiation of heat photons, while minuscule, carried a tiny amount of momentum with it, because the main antenna was located on the front of the craft, pointed back towards Earth and the Sun. More of this heat was actually being emitted from the back of the spacecraft. This created a very slight recoil force, a photon thrust pushing the craft back towards the Sun, exactly mimicking the observed anomalous deceleration. It was thermal radiation, a purely classical effect that had been the culprit all along. Yet, even with this elegant and widely accepted explanation, the story of the pioneer anomaly remains a profoundly important clue. It serves as a powerful lesson in scientific humility. For years, the greatest minds in physics were ready to rewrite the textbooks based on a discrepancy they could not explain, only to discover that the truth was a subtle effect they had simply overlooked. It reminds us that our instruments are not perfect observers. They are physical objects interacting with their environment in complex ways. The anomaly was a ghost in the machine, but it was our machine. This episode underscores a crucial principle. Before invoking the spectacular new dimensions, new forces, new laws of physics, we must first exhaustively check for the mundane. But it also leaves a tantalizing door open. What if the next anomaly, the next tiny deviation in a spacecraft's path, isn't so easily explained away? The pioneer anomaly taught us how to look more carefully, and in doing so, it sharpened our tools for discovering the next great mystery hidden in the quiet motion of the heavens. But our journey into cosmic anomalies now takes us from the subtle tug on our own spacecraft to a mystery of truly galactic proportions, one that threatens to unravel our most fundamental understanding of how the universe holds itself together. This clue isn't about a fleeting signal or a tiny miscalculation. It's about a ghostly presence that seems to permeate every corner of the cosmos, an invisible scaffolding that dictates the very motion of galaxies yet refuses to reveal itself. We are talking about the enigma of dark matter, and its story begins not in the void of deep space, but in the careful, patient work of a pioneering astronomer staring at the whirling pinwheels of distant island universes. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a massive gathering of thousands of galaxies. By measuring how fast these galaxies were moving around within the cluster, he could estimate the cluster's total mass based on the gravitational pull needed to keep them all bound together. What he found was startling. The mass required to account for the frantic speeds of these galaxies was hundreds of times greater than the mass that could be accounted for by all the visible stars, gas, and dust he could see. He called this missing mass Dunkel Materie, or dark matter. For decades, his work was largely ignored, considered an oddity, but the problem refused to disappear. In the 1970s, astronomer Vera Rubin provided the most compelling evidence yet, not from a cluster, but from within individual spiral galaxies. By meticulously mapping the rotation curves of stars on the outskirts of galaxies, she made a discovery that would forever change astronomy. According to Newton's laws of gravity, stars on the outer edges of a galaxy, far from the central bulge of mass, should orbit much more slowly, just as Pluto in our solar system moves far more sluggishly around the Sun than Mercury does. But that's not what Rubin found. To her astonishment, and to the continued astonishment of every astronomer since, stars at the very fringe of a galaxy orbit just as fast as those near the center. It's as if the entire galaxy is embedded within a gigantic, massive sphere of something invisible, a halo of unseen matter whose gravity is the dominant force, orchestrating the galactic dance from the shadows. The implications of this are staggering. Everything we see when we look at a galaxy, all the brilliant stars, the glowing nebulae, the vast clouds of cosmic dust, accounts for a mere 15% of the actual mass present. The other 85% is this invisible stuff, this dark matter. We know it's there because of its gravitational muscle. It shapes the largest structures in the universe, bending the paths of light rays in a phenomenon known as gravitational lensing, and providing the gravitational glue that holds entire clusters of galaxies together. And yet, despite knowing it's there, we have absolutely no idea what it is. It does not emit, absorb, or reflect any form of light or electromagnetic radiation. It is completely and utterly dark. It doesn't interact with the normal matter that makes up our world, our bodies, and our telescopes in any way other than through gravity. You could have a mountain of dark matter passing through you right now, and you would feel absolutely nothing. This profound disconnect has launched one of the greatest detective stories in the history of science. For decades, the leading candidate has been a hypothetical particle known as a WIMP, a weakly interacting massive particle. These particles would be heavy, slow-moving, and would only interact with normal matter through the weak nuclear force and gravity. Dozens of incredibly sensitive experiments have been built deep underground, in abandoned mines and tunnels, shielded from cosmic rays, all waiting for the once-in-a-lifetime ping of a dark matter particle bumping into an atom in their detector. But after years of searching, the results have been deeply frustrating. Nothing. Not a single definitive, universally accepted detection. Other candidates have been proposed, like actions, which are incredibly light particles, or even primordial black holes formed in the instant after the Big Bang. But so far, the evidence for any of them remains elusive. This persistent failure to find what should be the most common substance in the universe has led some physicists to propose a far more radical solution. What if dark matter doesn't exist at all? What if instead our understanding of gravity itself is wrong? This idea is known as modified Newtonian dynamics, or MN. It proposes that on the incredibly large, low acceleration scales of galaxies, gravity doesn't behave exactly as Newton or Einstein predicted. It becomes slightly stronger, providing the extra tug needed to explain the rotation of stars without needing to invoke any invisible matter. In many cases, MN does a surprisingly good job of matching the observed rotation of galaxies, but it struggles to explain other phenomena, like the observed gravitational lensing from galaxy clusters, which seems to require the presence of a lot of extra mass that MN cannot provide. So we are left at a cosmic impasse. The majority of the scientific community still believes dark matter is a particle, and that we simply haven't built the right experiment to catch it yet. But the possibility remains that we are chasing a ghost, and that the real answer lies in a fundamental rewrite of physics. This opens the door to even more speculative and breathtaking ideas. Could dark matter be evidence of matter from other dimensions bleeding into our own? Or perhaps it is the gravitational echo of a parallel universe existing just beyond our perception. The mystery of dark matter's invisible grip is perhaps the ultimate testament to the fact that the universe is dominated not by what we see, but by what we cannot see, a hidden architecture whose true nature remains one of the greatest puzzles ever presented to science. If the mystery of dark matter is a story about an unseen force holding the cosmos together, then our next clue is its bizarre and terrifying counterpart, a force that is doing the exact opposite, tearing the very fabric of the universe apart at an ever-increasing rate. This discovery was so shocking, so completely unexpected, that it ripped apart our standard model of cosmology and earned its finders the Nobel Prize. We are talking about dark energy, and its story begins with what astronomers thought was a straightforward, if melancholy, cosmic fact. the universe is expanding, but that expansion is slowing down. The logic was simple and seemingly unassailable. After the Big Bang, the universe exploded outward, and everything has been flying apart ever since. But gravity, the great cosmic glue, acts as a constant brake on this expansion. Just as a ball thrown into the air slows down as Earth's gravity pulls on it, the gravitational attraction of all the matter in the cosmos, stars, galaxies, gas, and even dark matter, should be relentlessly pulling on the universe, gradually slowing its outward rush. The ultimate question for cosmologists was not if the expansion was slowing, but by how much. Would there be enough matter for gravity to eventually halt the expansion and pull everything back in a big crunch? Or would the universe just coast forever, expanding at a slower and slower pace towards a cold, dark fade-out? To settle this, two independent teams of astronomers in the late 1990s set out to measure the deceleration using a specific kind of cosmic landmark, Type 1, a supernova. These stellar explosions are crucial because they are what scientists call standard candles. They all explode with nearly the same intrinsic peak brightness. This means that by measuring how dim they appear to us here on Earth, astronomers can calculate their distance with incredible precision. Furthermore, by analyzing the redshift of their light, how much it has been stretched to longer wavelengths by the expansion of the universe, they can determine how fast the supernova's galaxy was moving away from us at the time the light was emitted, billions of years ago. By comparing supernova from different distances and thus different eras in cosmic history, they could essentially map out the expansion rate of the universe over time. They were fully expecting to see that more distant, older supernova would show signs of a universe expanding faster in the past, confirming that the expansion was indeed slowing down. What they found instead sent a tremor through the very foundations of physics. The data told a story that was the complete opposite of what anyone had predicted. The more distant supernova were dimmer than they should have been if the universe had been expanding more rapidly in the past. This could only mean one thing: the expansion of the universe was not slowing down. It was speeding up, it was accelerating. This was akin to throwing that ball into the air and watching in stunned silence as it didn't just keep going. It shot away faster and faster into the sky, defying gravity entirely. Something was out there, a mysterious repulsive force acting against gravity, and it was winning. This something was given a name that reflects our profound ignorance of its nature: dark energy. The implications of this discovery are almost too vast to comprehend. Dark energy is now calculated to make up about 68% of the total mass energy content of the entire universe. Think about that for a moment. Everything we know and understand, every atom, every star, every galaxy, and even all the mysterious dark matter, accounts for less than a third of what's out there. The dominant force shaping the ultimate fate of the cosmos is this completely unknown entity. But what could it be? The leading, and in many ways the simplest, explanation is that dark energy is a property of space itself. Empty space, according to quantum physics, is not truly empty. It is a seething, bubbling foam of virtual particles constantly popping in and out of existence. This quantum vacuum is theorized to have an inherent energy density, often called the cosmological constant, a term Einstein himself introduced and then later discarded as his greatest blunder. This vacuum energy would exert a negative pressure, causing space-time itself to expand. The problem is that when physicists try to calculate the theoretical value of this vacuum energy, the number they get is wrong by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. It is arguably the worst prediction in the entire history of science. This colossal failure of theory has opened the door to other, even more mind-bending possibilities. Perhaps dark energy is not a constant, but a dynamic field that changes over time, a concept sometimes called quintessence. Or maybe it is evidence that our theory of gravity, Einstein's general relativity, breaks down on the very largest scales of the universe. The most profound speculation of all is that the acceleration could be a clue that our universe is not alone. Some theories suggest that the gravitational pull from other, parallel universes in a vast multiverse could be subtly influencing our own, manifesting as this repulsive force. If this is true, then dark energy is not just a mystery within our universe. It is our first, faint glimpse into a cosmic reality far larger and more complex than we ever dreamed. A reality where the emptiness of space is the most powerful and mysterious thing of all. Just as dark energy pushes the universe apart on the grandest scales, a mysterious and equally powerful force is pulling us together on a slightly smaller, yet still colossal, intergalactic stage. Our journey now takes us from the abstract force of dark energy to a tangible, yet hidden, point in the cosmos, a gravitational beacon so potent that it is drawing our entire galaxy, along with countless others, on a relentless journey through the void. This is the mystery of the Great Attractor, and its story begins not with a flashy signal, but with the careful mapping of the cosmic currents that guide the motion of galaxies. For much of human history, we viewed our galaxy as a relatively stationary island in the cosmos. But with advanced astronomy, we've come to understand that everything is in motion, caught in an intricate cosmic web of gravitational influence. Our Milky Way, for instance, is not floating still. It is moving at an astonishing speed of over 600 kilometers per second. For a long time, this motion was largely attributed to the pull of the nearby Virgo cluster, a massive gathering of galaxies. But as measurements became more precise, astronomers realized the Virgo cluster's gravity was only a small part of the story. There was something else, something far more massive and much more distant, exerting a gravitational tug on us and on thousands of other galaxies in our local region of the universe. This something was dubbed the Great Attractor. The problem and the core of this cosmic clue is that we can't actually see it. The direction we're all moving toward lies in the constellation of Centaurus, but that part of the sky is directly behind the dense, dusty central plane of our own Milky Way galaxy. This region is known to astronomers as the zone of avoidance, because the thick clouds of gas and dust effectively block our view in optical light, creating a blind spot that obscures almost 20% of the extragalactic sky. It's like trying to see a distant city while standing in the middle of a dense, foggy forest. You know something is out there based on other clues, but your direct line of sight is completely blocked. So how do we study something we cannot see? We observe its effects. Just as you can deduce the presence of the wind by watching the trees bend, astronomers have mapped the motion of thousands of galaxies in our local supercluster. By meticulously tracking their velocities and trajectories, they have created a cosmic flow chart, and all the arrows point toward this one gravitational epicenter. The sheer scale of the pull indicates that the Great Attractor must be unimaginably massive, with a gravitational influence equivalent to tens of thousands of Milky Way galaxies. The leading and most accepted theory is that it is not a single, bizarre object, but a massive confluence of matter known as the Norma cluster, which is itself part of an even larger supercluster of galaxies called Laniakea. In this view, our Milky Way is merely a suburb on the outskirts of this immense metropolitan cluster, and we are simply flowing along the gravitational watershed toward its dense central city. However, the story doesn't end there, and the Great Attractor hints at why this remains a compelling clue. Even after accounting for the visible mass of the Norma cluster, and the surrounding Laniakea supercluster, some analyses suggest there might still be a residual pull, a hint that there could be even more mass hidden behind the zone of avoidance than our current models predict. This opens the door to more speculative and thrilling ideas. Could the Great Attractor be an immense, unprecedented concentration of the very dark matter that dominates the universe? Perhaps it is a knot in the cosmic web where dark matter has pooled into a gravitational well of staggering proportions, pulling in everything around it. Or, venturing further into the realm of theory, some have pondered if such a powerful and hidden gravitational anomaly could be something even more exotic, a place where the fabric of spacetime is warped by phenomena we don't yet understand, or a gravitational lens of such magnitude that it hints at a structure beyond our current comprehension. While there is no scientific evidence for such fantastical notions, the very fact that a significant portion of our sky remains a literal blind spot forces us to acknowledge that some of the universe's biggest secrets might be hiding in plain sight, or rather, just out of sight, compelling us to develop new tools and new methods to finally lift the veil and see what truly lies in the heart. The Great Cosmic Pull. But if the Great Attractor hints at a hidden architecture of gravity on the cosmic scale, our next clue takes us to the opposite extreme, to the bizarre and counterintuitive world of the impossibly small, where the very concepts of space and distance seem to break down completely. This is the phenomenon of quantum entanglement, a concept so strange that even Albert Einstein, who helped lay its foundations, famously derided it as spooky action at a distance. At its heart, entanglement is a simple yet profoundly unsettling idea. Two particles can become linked or entangled in such a way that whatever happens to one instantly affects the other, no matter how far apart they are. This connection appears to happen faster than the speed of light, seemingly violating a fundamental rule of Einstein's own theory of relativity, which states that nothing can travel faster than light. It's as if you had two magical coins and you flipped one in New York to find it was heads, and at that exact same instant, the other coin in Tokyo, without any signal passing between them, was also forced to be heads. This isn't just a theoretical puzzle, it's a rigorously tested and confirmed fact of nature, and it forces us to question the very nature of reality itself. To understand why this is so revolutionary, we have to step back into the classical world we think we know. In our everyday experience, objects are separate and localized. A cup on your desk is in one specific place, and if you move it, that action requires time and energy to propagate. Information has a speed limit, but in the quantum realm, this common-sense view completely evaporates. When particles become entangled, they lose their individual identities and are described by a single, shared quantum state. They are no longer two separate entities but parts of a single, unified system. The spooky part is that measuring a property of one particle, say, its spin or polarization, immediately and irrevocably determines the state of its partner, even if that partner is now on the other side of the galaxy. Experiments have confirmed this again and again, separating entangled particles by hundreds of miles and still observing this instantaneous correlation. Crucially, this effect cannot be used to send a faster-than-light message with information, because the outcome of the measurement on each side is random until it happens. It's only by comparing the results later at light speed that the eerie correlation is revealed. But the fact that the correlation exists at all is what shatters our classical intuition. So what does this mean for our understanding of space? Einstein's relativity paints a picture of space as a static stage, a container within which events unfold. But quantum entanglement suggests this stage might be an illusion. The phenomenon of non-locality, This ability of particles to ignore vast distances implies that space is not the fundamental separator we believe it to be. Instead, it hints at a deeper, underlying reality where everything is interconnected in a way that transcends physical distance. In this view, the vast emptiness between stars and galaxies might not be empty at all, but filled with a hidden web of quantum connections, a foundational layer of reality where separation is merely an appearance. Some interpretations of quantum mechanics, like the pilot wave theory, suggest that particles are guided by non-local waves, while others, like the many worlds interpretation, avoid the spookiness by suggesting that every quantum possibility branches off into its own universe. But perhaps the most mind-bending implication is that space itself could be emergent, a projection from a more fundamental reality where concepts like here and there simply don't apply. Think of it like a hologram where a three-dimensional image is encoded on a two-dimensional surface. All the information about the entire image is present at every point on the surface. In a similar way, our seemingly three-dimensional universe of separate objects and vast distances could be a projection from a two-dimensional boundary where everything is connected and distance is meaningless. Quantum entanglement, this spooky action, might be the fleeting glimpse we get of that deeper, interconnected code from which the illusion of space is generated, revealing a universe that is far more holistic, strange, and wondrous than we ever imagined. But if quantum entanglement challenges our notions of space and separation, our next clue confronts us with a paradox so deep it strikes at the very heart of reality, suggesting that the universe might fundamentally operate like a cosmic computer with a strict set of rules that black holes seem to break with impunity. This is the black hole information paradox, and to understand why it's so deeply troubling, we need to start with one of the most sacred principles in all of physics. Information cannot be created or destroyed. Think of information not as data on a hard drive, but as the fundamental fingerprint of every particle in the universe. It's the complete set of properties that makes you and makes an electron, its mass, its charge, its spin, its quantum state. According to the unwavering laws of quantum mechanics, this information is forever conserved. It can be transformed, scrambled, and mixed up beyond all recognition, like burning a book to ashes. But in principle, if you had a sufficiently powerful computer and perfect knowledge of the laws of physics, you could reverse the process. You could take those ashes, the smoke, the heat emitted, and work backwards to reconstruct every single word on every page. The information is never truly gone, it's just converted into other forms. This principle is the bedrock of quantum theory, and it has never been observed to fail. Until we look at a black hole. Now enter the black hole, the ultimate rebel. According to Einstein's general relativity, a black hole is terrifyingly simple. It's a region of space where gravity is so intense that nothing, not even light, can escape its pull. The boundary of this point of no return is called the event horizon. If you were to fall in, general relativity tells us you would be ripped apart by tidal forces, and your mass energy would be added to the black hole, increasing its size slightly. But what happens to your information, the specific, unique quantum state that was you? Einstein's theory says it is irretrievably lost, vanished behind the event horizon, trapped forever in the singularity at the center. This wouldn't be a problem on its own, but it directly contradicts quantum mechanics, which insists that information must be preserved. The paradox sharpened to a point with the work of Stephen Hawking. He discovered that black holes aren't completely black. Due to quantum effects near the event horizon, they slowly emit radiation, a faint glow of particles now known as Hawking radiation. This radiation causes the black hole to gradually lose mass and eventually evaporate completely, vanishing in a final burst of energy, And here's the catastrophic problem. Hawking showed that this radiation is purely thermal. It's random noise, like the static on an old television set. It contains no information whatsoever about what fell into the black hole. So when the black hole finally evaporates, all the information about every star, every planet, and every person that ever fell in is seemingly erased from the universe. It's the equivalent of burning that book and having the ashes themselves vanish into thin air, leaving no trace whatsoever. This is the information paradox. Two pillars of modern physics, both incredibly well tested, give us two completely contradictory answers. Quantum mechanics says information must be saved. General relativity via black holes says it is destroyed. For decades, this was the most severe crisis in theoretical physics. Most physicists believe that the solution lies not in abandoning quantum mechanics, but in realizing that our understanding of black holes is incomplete. This has led to some of the most profound and revolutionary ideas in modern science. One leading solution is the holographic principle. This astonishing idea suggests that all the information that falls into a black hole is not lost inside it, but is instead encoded on its two-dimensional event horizon, the surface area that surrounds it. Think of it like a cosmic thumb drive. When a three-dimensional object falls in, its information is smeared out and stored as a kind of quantum pixelation on the two-dimensional surface. Then, as Hawking radiation is emitted, it slowly and subtly carries that information away, encoded in the correlations between the radiation particles. It would be like burning that book, but the smoke particles carry away a hidden, microscopic pattern that, if you could read it, would perfectly describe every word. The information was never truly lost. It was just translated into an incredibly complex code. If this is true, it suggests a mind-bending reality, that the three-dimensional universe we experience, with its depth and volume, might itself be a projection from a two-dimensional surface at the boundary of the universe. The black hole is just a stark example of this holographic nature, a place where the illusion breaks down and reveals the deeper code. Other theories propose that black holes don't have a singularity at their center at all, but that our equations break down before we reach it. Perhaps there is a hidden region of space-time, a Planck star or a wormhole that preserves the information, or maybe the information escapes through a connection to a parallel universe. While these ideas sound like science fiction, they are serious attempts to resolve a fundamental contradiction in our understanding of reality. The black hole information paradox is more than just a puzzle about cosmic vacuum cleaners. It is a powerful clue that space-time itself may not be the fundamental stage of the universe. It might be an emergent property, a secondary effect that arises from something deeper and far more strange, a reality where information is the true currency of existence, and the black hole is the ultimate test of its conservation. Just when we think we've mapped the grand architecture of the cosmos, from the quantum foam to the gravitational pull of the Great Attractor, the universe presents us with a clue so unnerving that it seems to challenge the very foundation of modern cosmology. This clue isn't a shadowy force or a fleeting signal. It's a ghostly pattern imprinted on the oldest light in existence, a pattern that appears to be looking right back at us in a way that defies all reasonable expectation. This is the mystery of the axis of evil, a name that perfectly captures the profound discomfort this discovery has caused within the scientific community. To understand why this anomaly is so deeply troubling, we need to go back to the very beginning, to a time when the universe was a seething, opaque plasma, just 380,000 years after the Big Bang. As this hot, dense soup of particles expanded and cooled, it finally became transparent, allowing light to travel freely for the first time. That first flash of light, stretched and cooled by 14 billion years of expansion, still fills the entire universe today. We detect it as a faint microwave hiss coming from every direction in the sky, the cosmic microwave background, or CMB. This radiation is the baby picture of the cosmos, and it is the single most important piece of evidence we have for the Big Bang theory. Crucially, this background is incredibly uniform, with a nearly perfect temperature of just 2.7 degrees above absolute zero everywhere we look. But when you look with exquisite precision, you see tiny, minuscule fluctuations, variations in temperature of just 1 part in 100,000. These tiny ripples are the seeds of all future structure, the gravitational blueprints from which every galaxy, star, and planet would eventually form. The foundational assumption of modern cosmology, called the cosmological principle, states that on the very largest scales, the universe is isotropic and homogeneous. This is a fancy way of saying it should look the same in every direction and have no preferred center or special axis. There should be no up or down in the cosmos. The patterns in the CMB fluctuations should be completely random, like a static-filled television screen, with no large-scale patterns or alignments. This principle is the bedrock upon which our entire understanding of the universe is built. But then, we built satellites like NAS, a Wilkinson microwave anisotropy probe, and the European Space Agency's Planck Observatory to map this background radiation in unprecedented detail. And that's when they found the anomaly. Scientists analyzing the Planck data noticed something that should not be there. The largest scale fluctuations in the CMB, the biggest ripples in the fabric of spacetime, were not randomly oriented as expected. Instead, they appeared to be aligned along a specific axis, a particular direction in space that seems to be strangely correlated with the plane of our own solar system and the direction of the sun's motion through the galaxy. It's as if the universe's largest scale structure has a subtle preference for a certain orientation, and that orientation just happens to be linked to our little corner of the cosmos. This apparent preferred direction was so shocking and so seemingly unnatural that researchers half-jokingly dubbed it the axis of evil, a name that stuck because it so perfectly conveys the threat this discovery poses to our standard models. The immediate and most likely explanation is that this is not a feature of the universe at all, but a systematic error in our observations. Perhaps there is some unknown foreground contamination, some subtle emission from dust within our own Milky Way galaxy that we haven't fully accounted for, which is imprinting this false pattern onto the primordial CMB data. Maybe it's an artifact of the complex methods used to process the raw satellite data and subtract out all the local interference. The teams working on the Planck data have tirelessly searched for such errors, and while they have been able to reduce the significance of the anomaly, they have not been able to make it completely go away. It persists, a stubborn and perplexing ghost in the data. If it is real and not an illusion, the implications are staggering. It would mean that the universe on its largest scales is not isotropic. It has a preferred direction, a kind of cosmic north. This would force a radical rewrite of cosmology, potentially requiring new physics that incorporates a fundamental directionality to spacetime itself. But the part that really fuels wild speculation is its apparent alignment with us. The so-called evil part of the axis of evil is this unsettling coincidence. Why would the largest scale structure of the entire universe, the echo of its creation, be aligned with the utterly insignificant plane of our solar system? From a purely random universe, the odds of such an alignment are astronomically low. This has led some to propose that we might be seeing a signature of something beyond our universe. Perhaps the gravitational pull of a neighboring universe in a vast multiverse is exerting a subtle tidal force on our own, imprinting a preferred direction onto the CMB. Or, even more radically, it could be a hint that the universe is not what it seems, and that these correlations are a kind of flaw in the simulation, a lingering artifact of the underlying code that generated our reality, a place where the programmer's coordinate system inadvertently bled through into the simulation. While these ideas are highly speculative, the axis of evil remains a profound and unresolved clue, a whisper from the ancient light that the universe might not be the random, centerless expanse we believe it to be, but a place with hidden structures and directions we are only just beginning to perceive. Yet, even as we grapple with the possibility of a universe with a preferred direction, a far more tangible and contentious mystery was brewing not in the depths of space, but in laboratories right here on Earth. This clue doesn't involve ancient light or distant galaxies. It centers on a seemingly impossible engine, a device that promised to rewrite the rules of spaceflight and, in doing so, challenged one of the most fundamental laws of physics itself. This is the story of the M-Drive, a concept so revolutionary and so controversial that it became a scientific firestorm, pitting bold ambition against rigorous skepticism. The principle behind the M-Drive is deceptively simple, and that is precisely what makes it so alluring. Every rocket engine ever built operates on Sir Isaac Newton's third law of motion. For every action, there is an equal and opposite reaction. To move forward, you must throw something backward. Chemical rockets throw out superheated gas. Ion thrusters throw out charged particles. Even a sailboat pushes against water, and an airplane pushes against air. The M-Drive, short for electromagnetic drive, proposed something radically different. It was a hollow, truncated copper cone sealed at both ends. When you pump microwave energy into this cavity, the waves bounce around inside, and according to its inventors, this bouncing creates a net thrust toward the wider end of the cone. No fuel is consumed, no propellant is ejected out of a nozzle. It simply pushes. If true, this would be nothing short of a miracle. It would be the physics equivalent of getting into a car, pushing on the dashboard, and making the entire car move forward. It violates the conservation of momentum, a cornerstone principle that has underpinned all of mechanics for over 3 centuries. The implications of such a device are staggering. A working M-Drive would utterly transform our future in space. Without the need to carry enormous tanks of fuel, spacecraft could be lighter, cheaper, and far more efficient. Trips to Mars could be cut to a matter of weeks. Probes could reach the outer solar system in years instead of decades. It could, in theory, open the door to practical interstellar travel, all with a device that has no moving parts and runs on electricity, which we can generate easily with solar panels. It's the dream of a reactionless drive, a staple of science fiction from Star Trek to The Expanse, seemingly made real in a laboratory. The controversy ignited when several research teams, including a small group at NASA's Eagleworks laboratory, reported that in their carefully controlled experiments, they were indeed measuring a tiny but persistent thrust from their M-Drive prototypes. The reported force was minuscule, on the order of micronewtons, about the same force as the weight of a small ant, but it was consistently there, and it defied their initial attempts to explain it away. The scientific community reacted with intense skepticism, as it absolutely should have when faced with a claim that overturns fundamental physics. The hunt for errors began. Critics pointed out numerous potential sources for false positives. Could it be thermal expansion? As the copper cavity heats up from the microwaves, it might expand ever so slightly, shifting its center of mass and mimicking thrust. What about the interaction of the device's powerful magnetic fields with the Earth's own magnetic field? Perhaps it was an experimental artifact known as the Lorentz force. Or maybe the thrust was coming from the electrical wires feeding the device, or even from air currents inside the vacuum chamber acting on the heated device. Each time a potential error was raised, proponents of the drive worked to design new experiments to rule it out. They built better isolation systems, used more precise measuring instruments like torsion pendulums and force sensors, and even ran tests in near-perfect vacuums. And yet, some groups still reported that tiny, stubborn thrust signal. The debate raged for years, not in the pages of newspapers, but in dense scientific papers and heated conference discussions. The central problem was that no one, not even the inventors, could provide a convincing physical explanation for how the M drive could work within the known laws of physics. Some ventured into the realm of highly speculative theory, suggesting it might be interacting with the quantum vacuum, the seething foam of virtual particles that pop in and out of existence in empty space. The idea was that the drive wasn't reactionless after all. It was pushing against this quantum foam. However, most physicists dismissed this, pointing out that the quantum vacuum cannot provide a reactive medium in the way required. It's a fundamentally different concept. Other theories involved manipulating inertia or tapping into hidden dimensions, ideas that strayed far from the mainstream. The saga reached a critical point when larger, more rigorous research groups entered the fray. Teams in Germany and at the Dresden University of Technology built their own incredibly sensitive M-drive test rigs, designed specifically to nullify every conceivable error source. Their results were definitive. They found that when they ran their experiments, they too measured a thrust signal. But then, crucially, they ran a null test. They configured their setup so that the thrust should be zero according to the theory. And they still measured the same signal. This proved conclusively that the thrust was not coming from the M-drive effect, but from an experimental artifact, most likely thermal effects in the device itself or its mounting. The thrust was real, but it was a measurement error, a mirage caused by the intense heat of the microwaves warping the apparatus. The scientific consensus now is that the M-drive does not work as advertised. It was a classic case of a persistent experimental anomaly, a ghost in the machine that fooled even careful researchers for a time. But the true value of the M-drive controversy is not in the device itself, which almost certainly doesn't work, but in the profound questions it forced us to ask. It challenged us to interrogate our own understanding with brutal honesty. It showed the immense difficulty of measuring vanishingly small forces and the ease with which our hopes can create blind spots in our data. More importantly, it served as a powerful thought experiment. What if such a drive were possible? What would that mean for our understanding of the universe? It pushed physicists to articulate exactly why conservation of momentum is so inviolable, deepening our appreciation for this fundamental symmetry of nature. The M-drive, in its failure, stands as a monument to the scientific process itself, a process that is messy, argumentative, and often slow, but one that is ultimately self-correcting. It reminds us that extraordinary claims require not just extraordinary evidence, but extraordinary scrutiny, and that sometimes the most exciting path forward is not in breaking the laws of physics, but in truly understanding them. Just as the M-drive controversy showed us how a tantalizing idea can capture our imagination before being soberly explained by conventional physics, our next clue takes us back out into the cosmos to a star that has become the poster child for unexplained astronomical behavior, a place where the line between natural wonder and science fiction becomes thrillingly blurred. This is the story of KIC 8,462,852, better known as Tabby star, or as it's often called in headlines, the most mysterious star in the galaxy. Its tail begins not with a sudden flash, but with a slow, puzzling fade, discovered not by a lone astronomer peering through a telescope, but by the unblinking digital eye of the Kepler Space Telescope and the sharp curiosity of thousands of citizen scientists. The Kepler mission was designed for one primary purpose: to find planets around other stars by watching for the telltale, periodic dimming that occurs when an exoplanet passes in front of its host star, blocking a tiny fraction of its light. These transit events are typically small, predictable, and rhythmic, like a perfectly timed clock. But amidst the torrent of data from hundreds of thousands of stars, a team of volunteers for the Planet Hunters project, led by citizen scientist and later namesake Tabetha Boyajian, found a light curve that looked like nothing else. This star, located about 1,400 light-years away in the constellation Cygnus, was doing something bizarre. Instead of the gentle, repeating dips of a planet, its light was fading in wild, irregular, and dramatic ways. There were small, frequent dips of 1 or 2%, but then there were the monumental drops. At one point, the star's light output plummeted by a staggering 22%. To put that in perspective, a Jupiter-sized planet, the largest in our solar system, would block only about 1% of a sun-like star's light. Something colossal was passing in front of Tabby's star, and it was unlike anything in our astronomical playbook. The immediate hunt for a natural explanation began. The first and most persistent theory involved dust, perhaps a massive, fragmented comet swarm or a huge cloud of fine-grained circumstellar debris was orbiting the star in a highly irregular and elliptical orbit, causing the bizarre dimming pattern. The problem was that dust, especially fine dust, should also scatter and absorb the star's light at different wavelengths, creating a specific signature in the infrared part of the spectrum. When astronomers pointed the Spitzer Space Telescope at it, they found a puzzling lack of this excess infrared heat. Whatever was blocking the light was doing so in a way that was largely opaque, meaning it blocked the light completely, but not like a typical dust cloud. Other ideas involved a recent planetary collision that threw up vast clouds of debris, or a family of shattered asteroids, but these events are thought to be incredibly rare, and the star's long-term behavior added another layer of mystery. Because the strangeness of Tabby's star wasn't just about its short-term dips, when astronomers delved into archival data, they uncovered another bombshell. An analysis of old photographic plates suggested that over the course of the last century, the star's overall brightness had also dimmed significantly, by as much as 14%. This long-term secular dimming was, if true, even more difficult to explain than the short-term dips. Stars of this type simply don't behave this way on such short timescales. They are stable for billions of years. While some later studies have questioned the certainty of this century-long fade, the debate itself highlights just how anomalous this object appears to be. It was this combination of bizarre, aperiodic dimming and the potential for a long-term trend that opened the door to the most famous and thrilling of all the speculations, the alien megastructure hypothesis. The physicist Freeman Dyson had once theorized that a sufficiently advanced civilization, needing vast amounts of energy, might eventually build a colossal array of solar collectors around its host star, a Dyson sphere or swarm. Such a structure, incomplete and under construction, would likely be irregular in shape and would cause exactly the kind of bizarre, non-repeating, and deep-dimming events that we see at Tabby's star. The idea was not that the star was entirely enclosed, but that we might be witnessing the shadows of the first stages of this unimaginable feat of engineering. This was not the preferred explanation of astronomers, but it was a scientifically valid, if remote, possibility that needed to be considered, and it catapulted this obscure star into the global spotlight. The subsequent scientific investigation has been a masterclass in modern astronomy, mobilizing telescopes across the globe and in space. When a major dipping event was detected in 2017, the call went out, and within hours, observatories worldwide were trained on the star, collecting data across the entire electromagnetic spectrum. The key finding was that the dimming was more pronounced at blue wavelengths than at red ones. This is a classic signature of dust. Smaller particles scatter blue light more effectively. This strong evidence pointed firmly away from solid, opaque megastructures, which would block all light equally, and toward some kind of non-uniform dusty material. The current leading theory is that the star is surrounded by a vast, irregular cloud of extremely fine dust, perhaps from the breakup of a giant comet or a family of moon-sized objects, which causes the deep, irregular dips. The long-term dimming could be explained by a larger, recent collision that created this cloud, which is now slowly dispersing. Yet, even with this compelling, dusty answer, Tabby's star retains its aura of mystery. The precise origin and nature of this dust, and why it seems to behave in such a uniquely chaotic way around this particular star, are still active topics of research. It serves as a powerful reminder that nature is often more creative and bizarre than our wildest fiction. We went looking for planets and found a puzzle that, for a beautiful moment, allowed us to dream of civilizations among the stars, but which ultimately taught us that there are still profound and natural wonders in the cosmos that we have yet to fully understand, reminding us that the universe needs no aliens to be utterly, breathtakingly strange. And just as Tabby's star taught us to expect the unexpected from our cosmic neighbors, the universe delivered a visitor that made all prior anomalies seem almost ordinary, an object that didn't just drift into our solar system, but screamed through it, leaving behind a trail of bewilderment and a stark reminder of how much we have yet to learn. This is the story of Oumuamua, the first known interstellar object to pass through our celestial neighborhood, and its brief, dazzling appearance shattered our expectations of what such a traveler should be. Its discovery in October 2017 was a milestone in itself. For the first time, we had definitive proof that objects from other star systems regularly cruise through our own. But Oumuamua, a name from Hawaiian meaning a messenger from afar arriving first, was anything but a simple space rock. From the very beginning, it defied categorization. Its path was hyperbolic, meaning it was moving far too fast to be bound by the sun's gravity. It was just passing through. As telescopes around the world swiveled to observe it, the peculiarities began to stack up. First was its shape. While we never got a clear picture, the way its brightness changed dramatically as it tumbled suggested an extremely elongated, cigar-like object, perhaps 10 times as long as it was wide. Nothing like this exists in our solar system, where asteroids and comets are generally more lumpy and spherical. This was our first clue that the geology, or perhaps even the technology, of other star systems could produce forms far stranger than anything we've seen at home. Then came the real shocker, its acceleration. As Oumuamua rounded the sun and began its journey back out into interstellar space, astronomers tracking its position noticed something impossible. It was speeding up, not just from the slingshot effect of the sun's gravity, but in a way that suggested an additional, non-gravitational force was acting upon it. For a comet, this is standard behavior. Heat from the sun vaporizes ice on its surface in a process called outgassing, and the jetting of this material acts like a natural rocket engine, giving the comet a push. But Oumuamua showed absolutely no signs of outgassing. There was no visible coma, the fuzzy envelope of gas and dust that surrounds a comet's nucleus, and no detectable tail of debris streaming behind it. It was accelerating in complete silence, as if propelled by an invisible hand. This was the anomaly that launched 1,000 theories, each more incredible than the last. The scientific community scrambled for a natural explanation. One of the most creative proposed that Oumuamua was a hydrogen iceberg. The idea was that in the cold, dense cores of giant molecular clouds, large chunks of solid hydrogen could form. As this iceberg neared our sun, the theory went, the intense heat would cause the solid hydrogen to sublimate, providing the thrust for acceleration without producing any visible dust or complex gases that our telescopes could detect. It was an elegant solution, but it had a major flaw. The interstellar medium is generally too warm for such fragile hydrogen icebergs to survive a journey of millions of years without evaporating long before they reached us. Another hypothesis suggested it could be a nitrogen iceberg, a chunk sheared off from a Pluto-like object in another solar system. This would be more robust, and the sublimation of nitrogen could potentially explain the acceleration. Yet, to get the amount of thrust observed, Oumuamua would have had to lose a tremendous amount of its mass, which again should have left some kind of detectable trace, a faint tail or a specific spectral signature that was never observed. The object remained stubbornly dark and silent throughout its passage. It was this persistent lack of a conventional explanation, this refusal to fit into any known box, that led to the most sensational and controversial theory proposed by Harvard astronomer Avi Loeb, that Oumuamua could be a piece of advanced alien technology, perhaps a light sail, a vast, thin sheet designed to catch the radiation pressure from stars for propulsion. Its unusual shape would be consistent with a sail, and the mysterious acceleration could be explained by the gentle but constant push of sunlight itself on such an enormous, thin structure. It wouldn't need outgassing, it would ride on light. Loeb argued we were perhaps too quick to dismiss an artificial origin, that we should consider the possibility that we had just witnessed a derelict piece of another civilization sailing through our system like a ship passing in the night. While the majority of the scientific community leans toward a natural, albeit exotic, origin, the true legacy of Oumuamua is not in proving any one theory, but in highlighting the profound limitations of our knowledge. It was a one-of-a-kind data point, here and gone before we could ever truly study it, a fleeting glimpse into the vast and varied population of objects traveling between the stars. Its very existence suggests that our solar system's collection of asteroids and comets may be just one sample of a much more diverse and strange galactic menagerie. Oumuamua challenges our tidy classifications and forces us to admit that when it comes to visitors from the great dark between stars, we truly have no idea what to expect next. While the strange acceleration of Oumuamua presents a mystery from the depths of interstellar space, one of the most enduring and familiar cosmic puzzles has been hanging in our night sky for all of human history, a silent companion whose most basic behavior has sparked curiosity and speculation for generations. We are talking about our own moon and its most famous quirk, the fact that we only ever see one side of it. This phenomenon, known as synchronous rotation or tidal locking, is a feature we take for granted, but when you stop to really think about it, it's a beautiful and incredible cosmic coincidence that begs a deeper question. Why does our moon always keep one face turned away from us in a perfectly synchronized dance? The standard scientific explanation is elegant and well understood. Tidal locking is a natural consequence of gravity's tireless work over billions of years. Imagine the moon in its early history, likely rotating at a different, faster rate. The Earth's gravity exerts a stronger pull on the side of the moon that is slightly closer to it. This creates a subtle, stretching force, a tidal bulge, on the moon, much like the moon creates tides on our oceans. As the young moon spun, this bulge wouldn't have pointed directly at Earth. The rotation would have dragged it slightly ahead. The Earth's gravity would then pull back on this misaligned bulge, acting like a gentle but constant brake on the moon's spin. Over eons of this gravitational friction, the moon's rotation gradually slowed down until it precisely matched its orbital period around Earth. Now, it takes the same amount of time to spin once on its axis as it does to complete one orbit around our planet, about 27 days. From our perspective, the job is done. The braking has ceased, and the system has reached a stable, energy-efficient equilibrium. This same process has locked many other moons in our solar system to their parent planets. Jupiter's large Galilean moons are all tidally locked, for example. So, the mechanism itself is not unusual, but the moon's story is far from a simple case of a settled orbit. Its very existence is the first mystery. The leading theory, the giant impact hypothesis, suggests that early in Earth's history, a Mars-sized protoplanet named Theia collided with the young Earth in a cataclysmic event. The debris from this incredible impact was flung into orbit around Earth and eventually coalesced to form the Moon. This theory elegantly explains key evidence, like the fact that the Moon has a surprisingly small metallic core compared to Earth, as if it was formed from the outer layers of both bodies. It also accounts for the similar isotopic compositions of rocks on the Earth and Moon, suggesting a shared origin. Yet, this violent birth story is so dramatic, so perfectly calibrated to create the Moon we have, a satellite unusually large relative to its planet, that it can feel almost too perfect, a cosmic accident of just the right kind. This sense of a too perfect moon is amplified by its other strange characteristics. Not only is it tidally locked, but its size and distance from Earth are also bizarrely precise. The moon is just the right size and at just the right distance to perfectly cover the sun during a total solar eclipse. This is a stunning celestial coincidence that occurs nowhere else among the planets and their moons in our solar system. Furthermore, the side of the moon we never see, the far side, is dramatically different from the familiar near side. The near side is covered in vast, smooth, dark plains of hardened lava called Maria, which form the man-in-the-moon pattern. The far side, however, is much more rugged, pockmarked with craters, and has very few of these dark Maria. Why would the two faces be so different? Scientists believe this asymmetry might be due to the Earth's gravitational influence and a thicker crust on the far side, but the stark contrast adds another layer of intrigue to our celestial partner. It is this combination of unique and finely tuned attributes that has, for decades, fueled more speculative and unconventional theories. In the 1970s, two Soviet scientists proposed the fission theory, suggesting the moon was once part of the Earth and was spun off from the rapidly rotating Pacific Basin. While this idea has largely fallen out of favor due to geological evidence, it reflects a long-held intuition that the moon is deeply connected to us. More radically, in his 1970 book, Who Built the Moon?, authors Alan Butler and Christopher Knight explored a series of mathematical anomalies, suggesting the moon's dimensions and its relationship to the sun and Earth encode a precise and intentional geometry. They and others have pointed out that the moon's diameter is exactly 400 times smaller than the sun's, and it is also exactly 400 times closer to Earth than the sun is, hence the perfect solar eclipse. While scientists attribute this to a fascinating coincidence for some, the numbers feel like a signature. The most famous, and certainly the most sensational, of these alternative theories is the idea that the moon could be artificial, a hollow construct or an ancient spacecraft placed in orbit by a vastly advanced civilization. This concept was popularized by Russian authors Mikhail Vasin and Alexander Ashcherbakov in a 1968 article titled, "Is the Moon the Creation of Alien Intelligence?" They argued that the Moon's resilience in the face of massive asteroid impacts, not shattering but forming shallow craters, suggested an incredibly tough, metallic inner shell. They proposed it was a hollow, planet-like vessel sailed into place eons ago. Mainstream science thoroughly dismisses this. Seismic data from Apollo missions shows the Moon has an interior structure, including a core, though it is smaller and lighter than Earth. The ringing like a bell after a module impact is a myth. The seismic vibrations were entirely consistent with a solid, rocky body. Yet, the persistence of these ideas speaks to a deeper truth. The Moon, in its silent, constant, and perfectly synchronized presence, occupies a unique place in the human psyche. It feels personal. It feels designed for us. Science provides the robust, evidence-based answers of tidal forces and a violent collision. But the Moon's serene face continues to invite wonder, urging us to look up and ponder whether its perfect syncopation with our world is simply a happy accident of physics or a hint of a deeper, more mysterious cosmic harmony we have yet to fully understand. While we gaze in wonder at distant stars and mysterious interstellar objects, one of the most profound and personal clues in our quest to understand the cosmos comes from a world much closer to home, a world where humanity has actually touched the soil and conducted experiments in search of our most fundamental question: are we alone? This clue takes us back to the stark, rust-colored plains of Mars and the summer of 1976, when two robotic pioneers, Viking 1 and Viking 2, became the first spacecraft to successfully land on the Red Planet and perform the most sophisticated search for extraterrestrial life ever attempted. The results they sent back did not provide a simple answer. Instead, they created a puzzle so complex and so controversial that it continues to spark debate nearly 5 decades later. The Viking landers were marvels of their time, equipped with a suite of biology experiments designed to detect metabolic activity in the Martian soil. The most famous and promising of these was the labeled release, or LR, experiment, masterminded by engineer and inventor Gilbert Levin. The concept was elegant in its simplicity. A small sample of Martian soil would be scooped up by the lander's robotic arm and placed into a chamber. Then, a nutrient soup, rich in organic compounds and tagged with a radioactive carbon-14 tracer, would be added. The idea was that if any microorganisms were present in the soil, they would consume the nutrients, metabolize them, and then exhale or excrete them as a gaseous waste product. This waste gas, now containing the radioactive carbon tag, would be detected by a sensor. It was a test designed to find a breath, a whisper of metabolism. And to the astonishment of Levin and his team, the experiment worked. Almost immediately after the nutrient was added, the LR instrument registered a significant release of radioactive gas. It was a positive result. The experiment was run multiple times on both Viking landers, thousands of miles apart, and each time the same dramatic signal appeared. For a brief, exhilarating moment, it seemed that humanity had its first evidence of life on another world. But science demands rigor and replication, and the story quickly grew more complicated. Another instrument on board, the gas chromatograph mass spectrometer, was designed to search for the very building blocks of life, organic molecules. It found nothing, not a single trace. This was a devastating contradiction. How could there be life metabolizing nutrients without leaving behind any organic material, the essential stuff of life itself? The consensus within NASA quickly shifted away from biology. The official explanation became that the positive LR result was likely caused by a strange, non-biological chemical reaction in the highly oxidized Martian soil. The leading candidate was the presence of a powerful oxidizing agent, like hydrogen peroxide or superoxides, which could have broken down the nutrient solution and released the gas through pure chemistry, mimicking the signature of life without any life actually being present. This interpretation became the dominant narrative, and the dream of finding life on Mars was set aside for a generation. Yet, for Gilbert Levin and a growing number of scientists who have re-examined the data, the case was never truly closed. They argue that the evidence for life was dismissed far too quickly. Levin maintained until his passing in 2021 that the LR experiment had, in fact, detected microbial life. His supporters point out that the LR response was rapid and strong, exactly as one would expect from biological activity, and that it exhibited a classic life-like response when the experiment was run a second time on the same sample. The second injection of nutrient produced a much smaller gas release, as if the microbes had already consumed the available food from the first injection and were either satiated or had been killed by the process. This is a classic signature of a biological system, not a simple chemical one. Furthermore, they contend that the GCMS instrument might not have been sensitive enough to detect the low levels of organic material that would be present in a sparse microbial population, especially if that life was based on different chemistry than life on Earth. The recent discoveries by the Curiosity and Perseverance rovers have only added fuel to this debate. We now know that the Martian soil does indeed contain complex organic molecules, and that the surface is not uniformly hostile to life as once feared. The new data doesn't prove the Vikings found life, but it completely invalidates the primary reason that evidence was rejected in the first place. The enduring ambiguity of the Viking life detection experiments is a clue that operates on two profound levels. First, it forces us to confront the possibility that we may have already found evidence of life beyond Earth, but lack the context or the courage to recognize it. Our tools and our theories in the 1970s were built on a terrestrial understanding of biology. We were looking for life as we know it, and we may have been utterly unprepared for life as we don't know it. The second, and perhaps more important, lesson is about the nature of Mars itself. The Viking results, in all their confusing glory, paint a picture of a world that is chemically complex and active. The strange oxidizing chemistry proposed to explain the results suggests that Mars possesses a unique and alien geochemistry that we are still striving to understand. This environment, while harsh, could potentially support extremophile organisms' life that thrives in conditions we once thought were impossible. The Viking landers may not have given us a definitive yes or no, but they handed us a map to a much deeper mystery, one that continues to guide our exploration and reminds us that the answer to the question of life on Mars may still be sitting in that 40-year-old data, waiting for us to look at it with new eyes and a broader mind. But just as we search for life on the dusty plains of Mars, a far more ethereal and subtle mystery hangs in the skies of our own planet, a celestial phenomenon so delicate that most people have never even seen it, yet it may hold profound secrets about the hidden architecture of our solar system. This is the enigma of the zodiacal light, a faint, elusive glow that has puzzled astronomers for centuries, not because of its existence, but because of its surprising and unexplained intensity. For those who have been fortunate enough to witness it under perfectly dark, clear skies, the zodiacal light is a breathtaking sight. In the hour after twilight fades in the west, or just before dawn begins to lighten the eastern horizon, a soft, faintly glowing pyramid of light appears to rise from the point where the sun has set or is about to rise. This pyramid, tilted along the path of the ecliptic, the same plane in which the planet's orbit, is often described as a false dawn or a lingering twilight, but it is something far more cosmic. This gentle radiance is sunlight, reflected and scattered by countless billions of tiny dust particles that form a vast lenticular cloud permeating the inner solar system, a cloud so immense that it stretches from the orbit of Mercury out past Mars. We are, in a very real sense, living inside a gigantic interplanetary dust bunny. For a long time, the source of this dust seemed straightforward. The primary suspects were comets and asteroids. As comets swing around the sun, their ices vaporize, releasing trapped dust and grit that gets strewn along their orbital paths. Similarly, when asteroids collide out in the belt between Mars and Jupiter, they grind each other down, creating immense clouds of fine debris that can slowly spiral inward toward the sun due to a subtle drag force called the Poynting-Robertson effect. This constant rain of dust should, in theory, account for the zodiacal light we see. But when scientists began to carefully measure the total amount of light being scattered, the overall brightness and intensity of this glow, they ran into a serious problem. The numbers didn't add up. The known population of comets and asteroids, diligently catalogued and modeled, simply does not produce enough dust to account for the brilliant pillar of light we observe. There is a significant excess, a surplus of dust for which we have no clear origin. It's as if we calculated the amount of water flowing into a reservoir from all known rivers and streams, only to find the reservoir is much fuller than it should be, hinting at a hidden spring we haven't yet found. This discrepancy has sent scientists searching for that hidden spring, for the missing source of all this interplanetary dust. One compelling theory points the finger at Mars. The Martian moons, Phobos and Deimos, are small, dark, and heavily cratered objects, widely believed to be captured asteroids. They are constantly bombarded by micrometeorites, and their weak gravity would allow the dust kicked up from these impacts to easily escape into space, potentially providing a steady stream of new material to the inner solar system. Other researchers have looked further out to the Jupiter family comets, a large group of comets with short orbital periods, suggesting their contribution might have been underestimated. But while these are plausible contributors, the puzzle is so persistent that it has opened the door to far more exotic possibilities. Could there be an entirely unseen population of objects lurking in the inner solar system? Perhaps a previously undetected family of dark, dusty asteroids, orbiting closer to the sun than we usually look, is constantly grinding itself down and replenishing the cloud. Or maybe the dust itself is different than we assume. Some scientists have proposed that a fraction of this zodiacal dust might not be ordinary rocky material at all, but could be composed of exotic particles like magnetic monopoles or even particles of dark matter, though these ideas remain highly speculative. The most tantalizing possibility is that we are witnessing the ongoing disintegration of a large, yet-to-be-discovered object. In 2021, astronomers found evidence of a dusty debris ring sharing Venus's orbit and another associated with Mercury. Could there be more such rings, or even the ghostly remnants of a shattered planet, slowly spreading its dust across the solar system? The zodiacal light, this softest of glows, is therefore much more than a pretty light show. It is a forensic tool. By studying its spectrum, its polarization, and its distribution, we are essentially taking a core sample of our solar system's dust population, analyzing the forensic evidence of billions of years of collisions and disintegration. Its unexplained brightness is a quiet but persistent clue that our census of the inner solar system is incomplete, that hidden between the orbits of the planets, in the vast spaces we once thought were empty, there are unseen structures and unknown processes still waiting to be discovered, reminding us that even in our own celestial backyard, mysteries linger in the faintest of lights. Yet, even as we map the delicate glow of dust within our inner solar system, the mysteries only deepen as we venture outward to the cold, dark frontier where the sun's influence wanes and our charts of the cosmos simply end. This brings us to one of the most tantalizing structural clues in our own celestial backyard, the strange and abrupt edge of the Kuiper belt, a boundary so sharp and unexpected that astronomers have nicknamed it the Kuiper Cliff. For context, let's picture our solar system not as a simple set of planet orbits, but as a series of concentric rings and zones, each with its own unique population of objects. Beyond the orbit of Neptune lies the Kuiper belt, a vast disk of icy remnants left over from the solar system's formation. Think of it as a much larger, much colder cousin to the asteroid belt, home to dwarf planets like Pluto, Haumea, and Makemake, along with countless smaller ice rocks. For decades, our models of solar system formation have predicted how this belt should be structured. As you move away from the sun, the number of these objects should gradually decrease. The density of this frozen debris field should thin out slowly and smoothly, eventually fading into the emptiness of interstellar space. It should be a gentle slope, not a sharp drop-off. But that is not what we see. Around 50 astronomical units from the sun, that's 50 times the distance from Earth to the sun, something bizarre happens. The Kuiper belt doesn't gradually fade away. Instead, the population of detectable objects plummets. It's like carefully mapping a sprawling city and finding that the suburbs extend for miles, but then you suddenly reach a literal cliff edge, beyond which there are almost no houses at all. This isn't a small statistical glitch. It's a dramatic and unexplained termination of what should be a thriving community of icy worlds. Our telescopes can peer far beyond this point, and they do find a few scattered objects, like the dwarf planet Sedna with its bizarre, elongated orbit, but the thick, main concentration of the belt just stops. This is the Kuiper Cliff, and its existence is a direct challenge to our understanding of how our solar system was built and what surrounds it. So what could have soared off the edge of our solar system? Astronomers have proposed several compelling theories, each more fascinating than the last. The most headline-grabbing idea is the existence of a yet undiscovered planet, often referred to as Planet 9 or Planet X. This hypothetical world would be a super-Earth or a mini-Neptune, several times the mass of our own planet, orbiting the Sun hundreds of times further out than Earth does. The gravitational influence of such a massive object could very well be acting as a celestial shepherd, clearing out its orbital neighborhood and gravitationally ejecting any smaller objects that wander too close, thus creating that sharp, clean edge we observe. The gravitational clues for this planet are not just based on the cliff. They also come from the strange, clustered orbits of several extremely distant objects like Sedna, which all seem to be shepherded in a similar direction, as if being guided by an unseen master. But a hidden planet isn't the only possible architect of this cliff. Another possibility takes the source of the disturbance entirely outside our solar system. Our Sun, like all stars in the galaxy, is on a journey around the Milky Way's center. On this long cosmic trek, it's possible that we passed relatively close to another star millions of years ago. The gravitational tug from this stellar interloper could have ripped through the outer Kuiper belt, stripping away a huge swath of objects and hurling them into the depths of interstellar space, leaving behind the stark boundary we see today. It would have been a fleeting encounter, but its scars would remain frozen in time. Alternatively, the culprit might not be a star, but the persistent, gentle pull of the Milky Way's overall gravitational field, which could slowly erode the outer reaches of the belt over billions of years. There is also a chance that the cliff is not a true edge at all, but an observational illusion. the objects in the far Kuiper belt are incredibly faint and difficult to detect. It's possible that there is a second, more distant ring of icy bodies, but that they have been darkened over billions of years by radiation from the sun, their surfaces covered in a layer of ultra-black, complex organic compounds that make them nearly invisible to our current surveys. We wouldn't be seeing an end to the material, but merely a transition into objects too dark for us to easily find. The Kuiper Cliff stands as a humbling reminder that even the most familiar parts of our cosmic address can hold profound secrets. It tells us that our inventory of the solar system is still incomplete, and that the gravitational story of our neighborhood is still being written. Whether the answer is a new planet, a ghostly stellar passage, or something we haven't yet conceived, this abrupt edge in the ice is a powerful clue that the history of our solar system is far more dynamic and eventful than the serene model of planets orbiting in peaceful isolation would have us believe. Yet as we ponder the grand architecture of our solar system's outer edge, we are reminded that the greatest mysteries often lie not in the vastness of space, but in the tiniest of particles specifically, in a cosmic accounting error involving one of the lightest elements in existence. This brings us to a clue that is less about what's out there and more about what should be here but isn't. It's a puzzle that takes us back to the very first minutes of the universe, to a process so precise we can calculate it with stunning accuracy, and yet the numbers still don't quite add up. This is the universe's lithium problem, and while it might sound like a minor bookkeeping issue, it points to a potentially profound gap in our understanding of cosmic genesis. To appreciate the depth of this mystery, we need to rewind the clock to the absolute beginning. In the first 3 minutes after the Big Bang, the universe was an unimaginably hot and dense fusion reactor, rapidly cooling as it expanded. During this brief, explosive window known as Big Bang nucleosynthesis, the first atomic nuclei were forged from a primordial soup of protons and neutrons. The physics of this process is exquisitely well understood. We know the reaction rates, the cross-sections, and the conditions with such precision that we can predict exactly how much of each light element, hydrogen, helium, and trace amounts of lithium and beryllium should have been created. For hydrogen and helium, the predictions are spectacularly successful. The observed abundances in the oldest regions of the universe match the theoretical calculations almost perfectly, which is one of the strongest pillars of evidence we have for the Big Bang theory itself. But for lithium, the universe seems to have a glaring deficit. The calculations tell us that there should be about 3 times more lithium-7, the most common isotope, than what we actually find when we look at the oldest stars in our galaxy. These ancient stellar relics, known as Population 2 stars, are the perfect cosmic time capsules. They formed from nearly pristine gas that had been contaminated by little else beyond the elements created in the Big Bang. When astronomers use spectroscopy to analyze their atmospheres, they consistently find that the amount of lithium is only about 1/3 of what our models say it should be. It's as if the universe's original recipe for creation was followed perfectly for the main ingredients, but someone accidentally left out a crucial pinch of lithium. This discrepancy has sent physicists and astronomers on a decades-long quest for an explanation, and the suspects fall into 2 main categories. The first possibility is that our understanding of the nuclear physics in those first 3 minutes is somehow incomplete. Perhaps there were unknown nuclear reaction pathways that destroyed lithium as it was being formed, or maybe our models of the particle densities and temperatures during that frantic period are slightly off. Researchers have meticulously recalculated every known variable, tweaking reaction rates and exploring every conceivable loophole in the standard model of particle physics and cosmology. While some adjustments can nudge the predicted number a little, none have successfully closed the gap without breaking the perfect agreement we have for hydrogen and helium. The foundations of Big Bang nucleosynthesis are so robust that it's incredibly difficult to change the lithium yield without throwing the entire carefully balanced equation into chaos. This leads to the second and far more exciting possibility, that the lithium is being destroyed after the Big Bang, but before we get a chance to observe it in these ancient stars. But how and by what? These stars are the oldest things we can see. They are the very witnesses to the early universe. If lithium is being destroyed within them, it would require a previously unknown astrophysical process. Some theories suggest that certain types of exotic particles, like actions or other weakly interacting particles, could be produced in the cores of these stars, transporting energy outwards and stirring up the interior in a way that would bring the surface lithium down to the hotter core where it would be fused into heavier elements. Others have proposed that the pre-stellar gas clouds themselves might have had their lithium depleted by some mysterious early mechanism before the stars even formed. The lithium problem, though focused on a seemingly minor element, is a powerful reminder that our cosmic origin story, while incredibly successful, might still have a few missing pages. Lithium is the third element on the periodic table. Its behavior is dictated by the same standard model of physics that governs everything else. If we can't account for its simple abundance, it hints that there could be physics at play in the early universe that we haven't yet discovered. A subtle force or particle that left its fingerprint only on this one element. It's a small anomaly, but in science, the smallest inconsistencies often lead to the biggest revolutions. The lithium deficit is a quiet, persistent whisper from the dawn of time, suggesting that our narrative of cosmic evolution, for all its detail and grandeur, might still be missing a key chapter. Yet even as we grapple with missing lithium from the universe's first moments, a far more contemporary and pressing mystery has emerged, one that strikes at the very heart of our modern understanding of the cosmos and threatens to tear apart the very fabric of our standard cosmological model. This is the Hubble Tension, and it represents the most significant unsolved problem in cosmology today. At its core, it is a story of a simple number, the Hubble constant, that two different, incredibly precise methods of measurement stubbornly refuse to agree upon. It's a cosmic rift, a discrepancy that has grown only more pronounced with each new and improved observation, suggesting that our map of the universe's expansion might contain a fundamental flaw. To understand the stakes, we need to understand what the Hubble constant is. It's not just any number, it's the current expansion rate of the universe. It tells us how fast, at this very moment, galaxies are receding from us for each megaparsec of distance. A higher value means a faster, more frenetic expansion. A lower value points to a more sedate and leisurely pace. For decades, measuring this number accurately has been the holy grail of cosmology, because it doesn't just tell us about the universe's current state, it unlocks its entire history and determines its ultimate fate. There are two primary and supposedly independent ways to pin down this crucial number. The first method looks back to the ancient universe, to the afterglow of the Big Bang itself. By studying the detailed patterns in the cosmic microwave background, particularly with the Planck satellite, we can measure the conditions of the infant cosmos with exquisite precision. We can see the seeds of all future structure, and from that baby picture, we can run the universe's entire history forward through our standard model of cosmology, known as the lambda cold dark matter model. This model, which includes the effects of both dark matter and dark energy, spits out a prediction for what the Hubble constant should be today. This is a top-down, theoretical prediction based on the universe's beginnings. The second method takes a bottom-up, observational approach right here in the modern universe. This is the distance ladder method, famously used by Edwin Hubble himself, though now with far more advanced tools. Astronomers use incredibly reliable cosmic landmarks, like Cepheid variable stars and Type 1a supernova. These are standard candles, objects whose intrinsic brightness we know. By measuring how dim they appear to us, we can calculate their distance. Then, by measuring their redshift, how much their light is stretched by the expansion of the universe, we can directly calculate the current expansion rate. It's a straightforward, empirical measurement that doesn't rely on a grand cosmological model. It just measures what is happening right now. The problem, the tension, is that these two methods, both executed with breathtaking precision, give us two different answers. The Planck measurement of the early universe predicts a Hubble constant of about 67.4 kilometers per second per megaparsec. Meanwhile, the latest measurements from the distance ladder, led by a team using the Hubble Space Telescope and the magnificent new James Webb Space Telescope to painstakingly calibrate Cepheid variables, consistently find a higher value, around 73 kilometers per second per megaparsec. The difference might seem small, only about 5.6 kilometers per second, but the error bars on each measurement are now so incredibly tiny that this gap is statistically significant to a level of 5 sigma. In the world of physics, that's the gold standard for a real discrepancy. It means there's only a 1 in a million chance that this is a random fluke. This isn't a minor quibble, it's a direct contradiction. So what does this mean? The most thrilling possibility is that this tension is a direct signal of new physics. Our standard model of cosmology, the lambda-CDM model, has been spectacularly successful at explaining a vast array of observations, but the Hubble tension suggests it might be incomplete. Perhaps dark energy, the mysterious force causing the expansion to accelerate, is not a constant as Einstein proposed. Maybe it is dynamic, changing in strength over time. This concept, sometimes called early dark energy or phantom dark energy, could have altered the expansion history of the universe just enough to make the early and late measurements disagree. Other theories propose modifications to our understanding of gravity itself on the largest scales, or the existence of new types of relativistic particles that flooded the early universe and changed its evolution. Essentially, the Hubble tension could be our first empirical clue that there is an ingredient missing from our cosmic recipe, a shadow on the ledger of the universe's energy content that we haven't yet accounted for. Of course, the more mundane but still crucial possibility is that this is not new physics at all, but a systematic error in one or both sets of measurements. Perhaps our calibration of the cosmic distance ladder isn't as rock solid as we think. Maybe there are unknown biases in how we measure the brightness of Cepheid stars or the distances to nearby galaxies that are used to anchor the entire ladder. Teams are working furiously to eliminate these possibilities, using new methods like gravitational waves from merging neutron stars, which provide a completely independent way to measure distances. If these new methods side decisively with one camp over the other, it will point squarely to an error in measurement. But if they instead land somewhere in the middle or continue to show the discrepancy, the case for new physics will become overwhelming. The Hubble tension is more than an academic debate. It is a stress test for our entire understanding of the cosmos, a crack in the foundation that either reveals a hidden flaw in our instruments or a doorway to a deeper, more complete theory of the universe. Deep within the heart of our own galaxy, a silent and invisible storm of unimaginable energy is raging, and for over a decade, astronomers have been trying to decipher its origin. This clue doesn't come from the distant edge of the cosmos, but from our very own celestial backyard, the bustling and chaotic center of the Milky Way. It was here, while mapping the sky in the most energetic form of light, that scientists stumbled upon a signal that simply shouldn't be there, a mysterious and persistent glow that has become one of the most hotly debated puzzles in modern astrophysics. This is the galactic center excess, a ghostly surplus of gamma-ray radiation that defies easy explanation and points to something strange happening in the darkest reaches of our galactic core. To understand what we're seeing, we first need to understand the tool that revealed it. The Fermi Gamma Ray Space Telescope, launched in 2008, is designed to see the universe in gamma rays, the most energetic photons in the electromagnetic spectrum. These are not the gentle rays of light we see with our eyes. They are produced by the most violent and extreme processes in the universe: supernova explosions, jets from supermassive black holes, and collisions of particles accelerated to nearly the speed of light. When Fermi turned its gaze to the center of our galaxy, it saw exactly what was expected: a brilliant and complex fog of gamma rays. Much of this emission could be explained by known sources, like the frenetic activity of a supermassive black hole named Sagittarius A star, and a population of spinning neutron stars called pulsars, which sweep the sky with lighthouses of radiation. But after painstakingly building a detailed model to account for all of these known contributors and subtracting them from the total signal, a startling residue remained. Like a photographer subtracting city lights from a picture of the night sky to reveal the faint glow of the Milky Way, researchers were left with an unexpected and unexplained excess of gamma rays, symmetrically distributed around the galactic center. It was a diffuse, glowing halo of energy with no obvious source, a cosmic question mark shining in the most powerful light imaginable. The hunt for an explanation immediately split into two compelling and opposing camps. The first and most thrilling possibility is that we are seeing the long-sought-after signature of dark matter itself. The leading theoretical candidate for dark matter is a class of particles known as WIMP, weakly interacting massive particles. According to this theory, these particles are their own antimatter counterparts. When two WIMP collide, they would annihilate each other in a flash of energy, converting their mass directly into other particles, which would then decay into a shower of gamma rays. The center of the galaxy is believed to be the most dense region of dark matter in the entire Milky Way, a vast, invisible cloud whose immense gravitational pull is what holds the entire galaxy together. It is the perfect place for such collisions to be frequent. The observed characteristics of the excess, its smooth distribution, its specific energy spectrum, and its spatial shape, match surprisingly well with what many models predict for the annihilation of a WIMP with a mass about 50 to 60 times that of a proton. If this interpretation is correct, the galactic center excess would be the first direct, non-gravitational evidence for dark matter, a monumental discovery that would open a whole new window onto the fundamental nature of the majority of matter in the universe. But extraordinary claims require extraordinary evidence, and the other camp has a far more conventional, yet still fascinating, explanation. They argue that the excess is not a sign of new physics, but a testament to our incomplete understanding of old astrophysics. The galactic center is a notoriously complex and crowded environment. The leading alternative culprit is a previously undetected population of millisecond pulsars. These are ancient neutron stars that have been spun up to incredible speeds by siphoning material from a companion star. They emit powerful, lighthouse-like beams of gamma radiation. Individually, they would be too faint and numerous for Fermi to resolve against the bright background, but collectively, their combined, unresolved glow could perfectly mimic the smooth, symmetrical signal that we attribute to the excess. It would be like looking at a city from a great distance at night. You wouldn't see individual streetlights, but you would clearly see the collective glow of the city itself. Supporters of this idea point to other regions like the inner galaxy's bulge, where Fermi has actually begun to resolve individual point sources that could be such pulsars, chipping away at the supposed excess. They argue that with more sensitive observations, the entire signal could eventually be explained away as these mundane, though spectacular, stellar corpses. The debate between these two ideas is more than just academic squabbling. It is a perfect example of the scientific process at work. Both sides are vigorously searching for a smoking gun that will tip the scales. For the dark matter advocates, that would be finding the same excess signal in other, quieter places that should also have dark matter, but are devoid of the messy astrophysics of the galactic center, places like nearby dwarf spheroidal galaxies that are believed to be heavily dominated by dark matter. So far, searches in these dwarfs have come up empty, which is a point for the pulsar team. Meanwhile, the pulsar proponents are hunting for the telltale sign of their theory, the detection of individual point sources within the excess region. If they can find enough faint pulsars to account for the glow, the case for dark matter weakens. The James Webb Space Telescope and next-generation radio telescopes are now joining this hunt, peering through the dust and chaos of the galactic center with unprecedented clarity. What makes the galactic center excess such a profound clue is that it is a win-win mystery for science. If it turns out to be dark matter annihilation, it would be a landmark achievement, one of the greatest discoveries in the history of physics, finally revealing the identity of the universe's dominant material. But if it is proven to be a population of pulsars, it is still a revolutionary find, revealing an entire new ecosystem of stellar evolution in our galaxy's heart that we never knew existed. It forces us to better understand the intricate and violent ballet of stars and physics at the core of the Milky Way. Either way, this unexplained glow reminds us that we don't have to look billions of light years away to find the cutting edge of cosmic discovery. Some of the universe's most compelling secrets are hidden in plain sight, radiating from the very center of our own galactic home, waiting for us to develop the eyes to see them clearly. After exploring the unexplained glow at our galaxy's heart, we arrive at perhaps the most profound and mind-bending clue of all, one that doesn't just question the nature of space, but the nature of reality itself. This is the simulation hypothesis, the staggering idea that our entire universe, from the farthest quasar to the feeling of the wind on your face, might not be a fundamental reality, but an impossibly sophisticated simulation, a kind of cosmic virtual reality running on some form of advanced computing infrastructure. While it sounds like the plot of a science fiction movie, this concept has moved from the fringes of philosophy into serious scientific discussion, and it's supported by a number of curious features of our reality that look an awful lot like the hallmarks of a programmed construct. The argument finds one of its strongest pillars in the uncanny mathematical nature of the universe. As physicists have probed deeper into the laws of nature, they haven't found chaos or arbitrary rules. They've discovered an elegant, consistent, and deeply mathematical code underlying everything. Gravity follows an inverse square law. Quantum particles behave according to the precise probabilities of wave functions. The universe appears to be written in a language of mathematics. This is strangely convenient for us, the observers, but it also raises a question. Why is it so perfectly describable and computable? If the universe were a simulation, its mathematical backbone would be the source code, the set of programmed rules that govern the behavior of every element within it. The fact that we can discover these laws through observation and calculation could be seen as us reverse engineering the program. Furthermore, just like in a computer simulation, our reality appears to have resolution limits. The Planck scale, the smallest possible unit of space, time, and energy, acts remarkably like a pixel size or a processing limit. You cannot measure anything smaller than a Planck length. It's as if the simulation has a fundamental data resolution beyond which it does not render, a telltale sign of a digital construct. This digital feel extends into the bizarre world of quantum mechanics, which behaves less like a smooth, continuous reality and more like a processor managing limited resources. The famous double-slit experiment shows that particles exist in a fuzzy state of probability, a superposition until they are observed, at which point they suddenly choose a definite state. This wave function collapse is eerily similar to a computational optimization technique called lazy loading. In a complex video game, the detailed textures of a distant mountain aren't rendered until you look at it, saving processing power. In our universe, the definite properties of a particle might not be calculated until they need to be observed, saving the vast computational resources that would be required to simulate every particle in a definite state all the time. The inherent indeterminacy at the quantum level, the idea that things aren't real until measured, could be a feature, not a bug, a sign of a system that only generates reality on a need-to-know basis. The hypothesis also offers a potential, albeit speculative, answer to the Fermi paradox we started with. If the universe is a simulation, the eerie silence could be explained by a simple programming choice. The simulators may have only populated a single planet with life, ours as a focused experiment or a form of entertainment, making the rest of the cosmos an elaborate but empty backdrop to save on processing power. This planetarium hypothesis suggests the stars we see are not other suns with their own planets, but mere projections on the celestial dome, a rendered background to make our simulated environment feel vast and authentic. Of course, this idea is met with deep skepticism, and rightly so. The most common counter-argument is that it is ultimately untestable and unfalsifiable. It makes no predictions that could prove it wrong, which is a cornerstone of the scientific method. Others argue that simulating a universe as complex as our own, with conscious beings inside it, would require an impossible amount of computational power, far exceeding the energy of an entire universe. However, proponents counter that the simulating civilization could be vastly more advanced than we are, operating on physics we can't comprehend, or that they might be running the simulation on a computer outside of our spacetime, unbound by our physical constraints. Some, like philosopher Nick Bostrom, have even formalized the argument, suggesting that if it is possible for a civilization to create such simulations, and if they have any desire to do so, then there would be a statistical likelihood that we are living in one of countless simulations rather than in the base reality. Whether you find the simulation hypothesis compelling or outlandish, its true value lies in the profound questions it forces us to ask. It challenges the very bedrock of what we consider real. It pushes us to look at the mathematical elegance, the quantum weirdness, and the apparent fine-tuning of the universe not as settled facts, but as potential clues to a deeper truth. This idea doesn't provide easy answers, but it expands the realm of possibility, inviting us to consider that the space we gaze into and the laws we discover might not be the foundation of existence, but merely the user interface of a reality so complex and advanced that its true nature remains, for now, hidden behind the screen. From the profound silence of the Fermi paradox to the pixelated possibility of a simulated reality, these 21 unwritten clues weave together a tapestry of cosmic mystery that fundamentally challenges our perception of the universe. They are not merely a collection of isolated anomalies or curious footnotes in scientific journals. They are interconnected whispers from the void, each one hinting that the cosmos is far more strange, dynamic, and multifaceted than the tidy, mechanistic model we've been taught. This journey through cosmic whispers and defiant data points reveals a universe that is not a static stage but a living, breathing, and deeply enigmatic entity, one that actively resists our attempts to fully categorize and comprehend it. This grand collection of mysteries serves as the most powerful reminder that science is not a dusty book of settled facts, but a vibrant and ongoing journey of discovery. It is a process built not on certainty, but on a beautiful, relentless curiosity. Each anomaly, from the subtle drag on a spacecraft to the inexplicable acceleration of the universe's expansion, is a gift to that curiosity. It is an invitation to look deeper, to question our most fundamental assumptions, and to embrace the humility that comes with recognizing the vast expanse of our own ignorance. The true mark of a scientific mind is not in having all the answers, but in having the courage to sit with the questions, to let the discomfort of not knowing fuel the search for a deeper, more nuanced truth. These clues teach us that the universe's greatest secrets are not hidden in the light of well-understood phenomena, but in the shadows cast by the things we cannot yet explain. Whether these puzzles ultimately point toward new layers of physics, hidden dimensions curled up at the smallest scales, the subtle engineering of an intelligence beyond our own, or even a reality rendered on a cosmic computer, their collective message is unifying and profoundly hopeful. There is so much more to learn. The adventure is far from over. In fact, it is just beginning. Every strange signal, every gravitational anomaly, every particle that entangles with its partner across the galaxy is a signpost pointing toward horizons of understanding we have not yet even dreamed of. The universe is not a closed puzzle waiting to be solved. It is an endless frontier, rich with potential and waiting to reveal its secrets to those who are bold enough to ask the right questions, patient enough to sift through the data, and imaginative enough to consider possibilities that lie beyond the edge of our current reality. The greatest discovery is not a single answer, but the realization that the search itself, the act of reaching into the unknown, is what truly expands our minds and defines our place in this wondrous cosmos. If this journey through the cosmos has left you with more questions than answers, then our mission here was a success. The universe is a story that is still being written, and your curiosity is what turns the page. To make sure you don't miss the next chapter, hit that like button. It tells the algorithm you're ready for more. And subscribe to the channel so you can join us as we continue to explore the furthest reaches of space, time, and possibility. But the conversation shouldn't end here. The comment section is your launch pad. We want to hear from you. Which of these 21 clues did you find the most convincing, the most bizarre, or the most terrifying? Was it the eerie silence of the Fermi Paradox, the structured elegance of a holographic universe, or the ghostly pull of the Great Attractor? Share your thoughts, your own theories, and let's build a community of cosmic detectives, piecing together the greatest mystery of all together. This isn't a conclusion. It's an invitation to look up and wonder, to question everything, and to never stop exploring. Thanks for watching, and we'll see you in the next video.